All right. Thank you everyone for joining this session. So it's my pleasure to welcome Shubhanjali as a speaker for the day. And as we all know that we are going to go a little deep on generative AI transformers. And we have Shubhanjali, who is currently a senior consultant at Acuity Labs. She is also one of the directors of Women Who Code Chennai chapter besides me. And she has completed her advanced business analytics from IIM Ahmedabad and natural language processing with deep learning course from Stanford University. So I think we should be geared up to listen to what she is going to convey today. So the stage is all yours, Shubhanjali.
Thank you so much, Pavitra. Thank you, everybody, for joining at this time. And I really hope that you guys understand or learn, or like I'm able to explain this in a way that I intend to. And I will try to keep this interactive. So, please unmute yourselves. Please feel free to unmute yourselves. Feel free to put it in the chat, because if we are all quiet, nobody will. I would not come to know if you've slept or if you're still there. So I would keep asking you questions, all of you. Okay. Okay, so let's start. So I'm assuming that we all know what generative AI is. Even if we join Zoom, right, on top we will see AI companion. So it'll just generate everything. It'll produce the text transcripts or all those things. So basically, generative AI is anything that it's creating new, anything that new it is creating, right? And now the main thing, suddenly it exploded last to last end 2022 was because of transformers and because of chat gpt. So let's understand what the entire thing is about. So let's get right into it. Okay, so what exactly are transformers, right? So not the Hollywood, that movie series, that is also transformers, that is correct. But here in generative AI, it is a very exciting family of machine learning architecture, right? So we have a lot of architectures, and this is a new kind of architecture which is very, very elegant, and it helps us in a lot of generation of things, right? So I think that is pretty simple and straightforward, right? This looks very simple. So it's truly breathtaking and such a beautiful piece of art, right? Right here. So this is what everything is built on. So I think we are clear, right? We can end the session. This is transformer. So, okay, anybody has any doubt, or are we good? Okay, just joking. So before we get into that, I'm assuming that we know about a neural network. It will be very important that we understand neural networks. So, would anybody like to unmute and just give a brief or whatever they know about neural network? Anything, whatever is the idea, it could be the biological one also. We have it in our brains. So, anything. If anybody would want to unmute and maybe speak about that. No? Anything on chat? What do you
Yes,
understand by neural network?
and I think we are very limited, and you can feel free to unmute. So it's going to be a kind of a closed group conversation.
Yeah, you can all probably unmute and let me, share your thoughts or whatever you understand from this.
Hi.
Okay. Yeah, please go ahead.
Yeah, so in biological terms, neural network is basically our nervous system that conveys information from outside environment to our brain so that we understand. It passes the information
Perfect.
on. Yeah.
Perfect. So the entire idea of this thing, when we started, like we thought that, okay, so this is how the brain understands everything. So we have a lot of input, visual input, then auditory input, different kinds of input, which we take inside, and then we try to translate it or work something, and then we have an output, we have an understanding key. This is this is that, right? So similar to that, how can we make a computer or a machine do something similar? So basically, this is how it started, that if we can have a similar structure for our machines. So the most basic form was called a perceptron, So it has a number of inputs, so which we also call features. So it will have a number of inputs, and each of which is multiplied by a weight, and the result is summed together with a bias parameter. So if you could see in this particular diagram, there would be X, Y, Z, and you will have weights, and then there will be an output. Now, if we just look at, just try to look at it outside of technology, like how we deal with our day-to-day things. For example, your output you already know. Suppose you already have a notion about something. Now you have certain inputs based on which you have a notion about something. Say you don't like a friend. Okay, so you have XYZ input why you don't like. There were past experiences, or maybe because your previous experiences which are not even related to the friend, but your output is that I don't like that particular person. But what if you can change your things in between so that your output will change. So basically the input remains the same, the output will not change, but you can change W0, W1 and W2 in between. And W0, W1 and W2 is simply the weights. So say X, Y and Z are the three incidents that happened. Now how much weightage are you giving to those incidents? Those three incidents happened. You are not changing the input. You are changing those three things happened, but based on the output, based on maybe tomorrow that person did something good for you, the output changed, so you can change the weights. So the way we can also go back and we can also change the things of what we understand. So what we are trying to do with a neural network is we already have an output and we already have input. You already know that 10 users like this movie. You know this is what they like. Now you want to create a model which if you run on 100 other users, you will know that based on whatever you trained it on, it will give you correct output. So our entire idea why we are doing anything is based on the data that you have, you need to make computer design a model so that when you feed that model on untrained data or the data which is completely new, so you will know, like for example, you are an Amazon user, you have bought in the past 1 year a few things, but when Amazon's catalog changes, it should know that these five products this particular person will buy. So that is the entire thing. We are trying to just create a model which will work on untested data, test data, which will come. So neural network is just one kind of a way in which we can do that. Then there are other things, but neural network I'm talking about because it is very important for transformers. Transformer is a kind of a neural network architecture, but neural network is a kind of machine learning model where we have different other models as well. Okay, so this was a very brief understanding of neural network. Now, when I say backpropagation, this is a very, very important concept, but I think it will be difficult if I just okay. So what happens is, like I was giving you that example of you not liking a particular person based on five incidents. Three of those may be related to that person, two of those may be your previous example with other people, but you have learned that these kind of people are like this. So you took that input and you thought this should be the output. So you have an idea. But you backpropagation means you might have made an error in judging also. Backpropagation means that that error you will keep sending back and you will keep changing these lines, these all these connections which are being made, right? These connections you will either strengthen or weaken. So you will, based on your output, you already have an output. You already know what you want. For example, if you had an English sentence here and a French sentence here and you wanted to translate. So you know that if your English sentence is I like ice cream, what is the French translation for that? So you know the output, you know the input. Now, for you to create a model which will effectively translate all English sentences into into French, you need to train it in a way that it will effectively take it and run on other English statements as well. So back propagation is basically, so the first time you'll feed that model, so first time you just create a very basic model with very arbitrary parameters. So any neural network will have, like I said, right, there were different weights, the W1, W2, W3 in the previous slide. So here you have inputs, you have an output. These weights you assign anything arbitrarily initially. You will just assign it based on anything. And then there is a bias also, which I have not added a bias parameter. It's not in the diagram. So all these four things you just take arbitrarily. Then you propagate it. You just do a feed forward. Basically, all those things, they just go through all the different layers here. and then the output comes, and you see the output is not correct. So what you do, you have an output from the model and you have the actual output. So you find out what is the error, what is the difference between them. And based on that error, if it is huge, like your model is very, very incorrect in giving you the translation, so it's not a good model still. So you will keep doing the back propagation. And what the back propagation does, whatever is the error, it will keep putting it in different of these connections, and it will keep tweaking these values till the time you get very, very close to your actual output that you want. So what we are doing, we have a neural network, and based on the loss function, what I just said about the difference between the prediction and the actual, we apply a loss function on that, and based on that loss, how much of data you lost. Basically, your model predicted something, but you wanted something else, so there was some loss. That is called a loss function. So based on that, so you are optimizing that loss. That loss should be as minimum as possible, so that when you go to other English sentences which need to be translated to French, they are as correct as they can be, right? So this is what back propagation is. So a very good model, you would want it to propagate errors until the time you see and you're happy with the output. This process keeps happening. Back propagation happens, then again feed forward happens, then back propagation. So this optimization keeps happening till your loss functions becomes low, so that your prediction and actual is very close and you are happy with the output. So these are the two concepts. So are we clear on these two? Don't sleep,
Yes.
please. Okay, just joking. Okay, so now that we know those two things, now we will just talk about transformers. So we know neural network. So transformer is a type of neural network only, where you will have the different inputs and you will have multiple hidden layers. So what I was saying previously, so all the magic happens in the hidden layers, you know. So you know the input, you know the output, you can't change that. You know, I like ice cream is the input, and you know the French translation is the fixed output, but you can change everything in between so that you reach from there to there. And these are just numbers. That is the magic here. Based on just the numbers and that mathematical equation and that dot product and you know the calculus chain rule, they keep all these calculations go on inside, and based on that the values of these different weights change, and based on that you come very, very close to your output, and your model predicts and performs very well. So transformer is also a neural network architecture. It'll have an input layer, hidden layer, and output. Now, before I go to exactly why transformers, before that also we were doing natural language processing. So basically, neural network we understood. Now there's recurrent neural network, which would take each and every word and sequentially, for example, if I have to do English to French, it will take I like ice creams. I, first word to French, like to French, ice cream to French. Sequentially, it is happening. So it's not that when I is happening, like is also happening. Only when I will finish translating, then it will come to like, then it will come to ice cream, and then it will translate. So recurrent neural network was something that was being used for language translation. We had convolutional neural network that was being used for image translation. Okay, now we are using transformers for both. So what happened? Why did it happen like that? So for example, sorry. So to translate a word from English to French, RNN would take each word and sequentially spit out French words. So what is the problem with that? So what happens is then when you have very large sequences of text, right? So by the time you reach the end of the paragraph, you will forget what happened in the beginning because there is no link in between the words. You are sequentially translating, and you know in language context is very important, right? So without the context, the language, because the same word can make different things. I have an interest in economics, and the interest rate increased. Interest remains the same, but the meaning of the word, the context is very important. So if you just keep doing sequential translation based on word, you are missing out the bigger picture, and it might result in error. And if they were sequential, that is the reason they were very hard to train. So even if you just increase the number of GPUs, it will not increase the training. You can't make things faster. The translation will not happen faster. The training will not happen faster. So it cannot be trained on that much data. So RNN was working fine. It was, we were using it for natural language processing, for doing things like sentiment analysis, for doing things like translation. It was being used. There were some errors, but then again, like we said, it's a neural network, so the model learns, right? But despite that, there were these issues that it was very difficult to train, and the context would be missing. You would not be able to get the context as well. So transformers changed everything. So how do transformers work? For that, I will go to this again, this beautiful thing. So what happens is that you have to think of it as like, there is an input. Let's think of chat gpt. Okay, so when you are putting any input prompt, you are giving it a prompt. So that prompt, what all stages should it go through before you are given the entire answer back? First thing is, the machine should be able to understand what you wrote. The second thing is, it should be able to understand the context. And then it will go and look into the model that it has within, and then it will give all those things back to you. So keeping RNN in mind, recurrent neural network, how was transformer different? So what happened is that you have an input, and then you do input embedding. What is an input embedding? Input embedding simply means translate each and every word to a number. Basically, you have to. So basically, the computer does not understand words like we do. It has no understanding of language and why. But if you have to teach it, you will give it, each and every word can have a digit, and they are, or a number, and this is how they are stored. So the entire vocabulary has input embedding. So it's a huge, this thing, input embedding is done. Then on top of that, there is positional encoding. That would mean that in your particular sentence, which word comes after which, that position is important. Then you pass it through attention feed forward, and this will come to now. Okay. So there were three main innovations and breakthroughs on top of RNN. So RNN is also a neural network. This is also a neural network. Then what changed? So positional encoding. So this is the idea that instead of looking at each word sequentially, you take each word in your sequence, and before you feed it to the neural network, you can slap a number on it. So you can just say that this, what is generally comes after what is your name, and not what name. So that positional, so you are also feeding the data about the position of the words to the neural network. You are just not feeding a single word. In other words, you store the info about the word order in the data itself. So this is something that you're feeding with the word order. So this is another vector. So basically, when you are giving the input, you are feeding one vector, full vector about the position of the word, one full vector about the different meaning of the word. Basically, okay, I think I have something in the end. So first I'll go through the theory, and then we will just see how it works in action, because it might be too much at once to understand. But just keep asking me questions. This might be a little tricky, but we will see it in action. So hopefully it will become better. So just understand for now that instead of just sequentially feeding words, we are giving it extra information. We are giving our network extra information. One is positional encoding, which means that where in relation to the previous words this particular word fits. This is my favorite book. Favorite should not come before this. Favorite, this is book. No, that will not make sense. So this entire information also you are feeding. Okay. And then when you train that data on a lot of text data, the model learns how to interpret all those positional encodings. So what you do, you first give it all this input, and the model has been trained on a lot of similar data, which a lot of positional encoding with a, over time it keeps getting these data. And so it understands that what is, what are, and the different context and all it understands. So in this way, the NN learns the importance of word order from the data, and this makes it easier to train than RNNs. And also, this is completely parallel. Like in RNN, we were doing each word sequentially. Here, multiple words, they are all done in parallel. Okay, now a very, very important concept, which is attention. Attention actually had, in fact, this entire transformer paper, which was developed by the people at Google in 2017, the entire paper is called Attention is All You Need. And this was, attention was there before also, but the concept called self-attention was something that completely changed the game. So now, for example, translate the below sentence in French. The European Economic Area and this, right? So now you see what is the thing in France. And now one bad way to translate is to translate each text one by one, because in French, some words are flipped. This economic, the words will be flipped, and also there are gender things. Like if this will be European, this will be female, but in India, sorry, in English, it will not be like that. So you cannot do just word by word. You need to know the neighboring context, economic area. So you need to see, okay, so it's area. So would it be masculine or feminine? So based on that, it would be here translated. So you need to know the context around. So this is where attention comes in. So we did two things. First thing we did was input embedding, that each and every word is to be represented by a number. Second, we did positional encoding, which means each and every word has to know where in the sentence it is. So you are also passing the information of the position of that word in a sentence as the input. Okay. And the third thing that happens in Transformer is attention, where you need to see the context or the relation of each and every word. The with European with economic with area, European with the economic and area, economic with European the and area. So each and every word, its relation with others, you will see. And then what you do, you will create a probability distribution which would tell you that the and European, them coming closer has more probability than whatever, say the and area would come closer in some other sentence. So based on this particular sentence, a probability table is created, right? So that is called attention, where you also are seeing the relation of each word with each and every word in that particular sentence. So these three things are very important, that is here in transformers. Okay, now this is too much of reading. I will do a little bit of reading, and just stay with me, because in the end we will see how all of this comes into action. So first we will go through the theory, then we will see the practical. So even if it is not making sense to you immediately, you ask me, or else when we go through the practical, you will see and then you can ask me. But just try and understand it from a non-technological standpoint. So if you see, how does the model know which words it should be attending to? So, like, not every word in every sentence is very important, right? Like, what is your name is not very important. Your name, that is very important. So how does it know? So it is something that it learns over time with data. By thousands of examples of French and English sentence pair, the model learns about gender, word or order, plurality. It'll learn over time. It'll learn. You can't, the first time itself, like even if you're teaching a 3-year old, or even if you are learning a new language, the first time you will not understand, but more and more you keep reading, say, French or Spanish, you will understand a lot more about everything. So similarly, any model, any neural network, so the more data it sees, the more it learns and corrects itself, and the more it gets better in understanding and doing the task. So self-attention was the real transformation. So attention was about aligning words, which is like good for translation. But with self-attention, we are trying to understand the underlying meaning. So if you understand the underlying meaning of a sentence, then you can do more than translation. You can do summarization, you can do generalization, you can ask questions from that, because you have made the machine learn the or understand the meaning of the sentence. So translation was good. At using attention, you can do translation very well. But when you do self-attention, you can also put other things. You just understand the entire context of the thing. So what is incredible about neural network with transformers is that they analyze tons of text data. They begin to build a representation or understanding of language automatically. So the model keeps becoming better. So it understands that programmers, the spelling is wrong here. The programmers is similar to software developers. So these synonyms and all, it will automatically keep adding. So you will not have to feed it, that, okay, these are similar, these are similar. So the better the internal representation of language these neural networks learn, the better they will be at any task, naturally. So that is why we see ChatGPT can, or any large language model, they can do so many tasks so well because of the self-attention mechanism. They have been able to understand whatever you are putting. They understand the essence of what you are putting, and then you can ask questions, ask them to generate things, summarize it, explain to a 5-year-old. You can do any number of things with that, right? Okay. So for example, you say, server, can I have the check? And looks like I just crashed the server. So self-attention allows the neural network to understand the word in the context of the words around it. So even though the words are the same, right? But self-attention will help it understand in the context. So you will now see for this particular statement, server and its relationship with each and every other word. And here you will see similarly server and its relationship with each and every word. And this way you will understand the context of the statement, and this will get stored in the model so that in future it will understand that the server and check meaning this is a server, and server and crashed meaning this is that. So when the model processes the word in the first sentence, it might be attending to the word check. So when it processes this, it attends to check with response, with respect to server. So then it gets the context, okay, server and check meaning this is the server. But in the second sentence, it will be like crash, it will pay attention to crash. So it will be like, okay, this is that server. So it is very important that we understand the context, right? So in the second, the model attempts to crash, insinuating that it is a machine. So this is how the model understands. So what happens is it helps neural network to disambiguate words. The words in English, we know they can be similar. Similar words can mean so many things, but it will help to disambiguate because it knows the context. It is not just focusing on one single word alone. It knows the things around it, and it recognizes part of speech and a lot of other things it can do. With that is why what makes it so powerful in understanding language, and you feel like you're talking to another human being because it does understand words and sentences and language at that level. Okay, this is like a novel here. I'm not going to read it. Basically, everything put together. So this one thing, so I wanted to touch upon that architecture part. It consists of an encoder and a decoder. So when I go to the first slide here, this one is an encoder and this one is a decoder. So in very short, if we just try to understand, so input came here, we input embedding, we translated into your that thing, numbers, like what each word means in the form of numbers, because the machine will understand numbers. Then we will pass the positional encoding. So this will be a vector, depending on what is the dimension of your input, this will be having that dimension, this will be the position. So all these things is sent as an input to multi-head attention. Multi-head attention, I will just tell you in short. Multi-head attention would be that each and every word, for example, you have a word interest, and then you will look at it in 4 different forms: interest as a noun, interest as a verb, interest as an adjective, interest as that. So multi-head attention would mean that this word can mean any of these things. So I'm telling it to you from a very very this maybe in upcoming sessions we can talk more about it, but I won't be able to cover everything. So these are the things. So multi-head attention is something which is getting the context but also getting the context better than single head attention. And then you add a normalize, then you feed forward network. It's like back propagation, but you're feeding it forward. You are after back propagation, you again go from input to output, then add and normalize, and then you send these values to multi-head attention of your output. So here the output already. Suppose this is an English statement. You did all these things with that English statement, and the translation. So you did the output also in output embedding of that also. And here also you have multi-head attention. The input of this encoder comes to this multi-head attention, the output of this multi-head attention comes here. Based on that, feed forward this that. Linear means it is still a matrix. You have to translate it into words, then you put softmax, and the probabilities come out. So the probabilities would be how close are you to your actual input, I like ice cream, versus French input output, and are we good? Are we able to give that output well? So this is what is a very, very top level view of how a transformer looks and works. So this is also a neural network. This is also a neural network. This is called encoder. This is called decoder. They both work together, and we get an output probability based on which we keep making our model better. Okay. So the architecture of a transformer consists of an encoder and decoder. The encoder takes an input sequence and processes it into a set of hidden representations, capturing the contextual information, like we saw, multi-head information or multi-head attention of each token in the sequence. Token would be I like ice cream. I is one token, like is one token, ice cream is one token. You can tokenize your statement. You can also tokenize it differently, not every word, but then for the ease of understanding, I am tokenizing it as word by word. I like ice cream can be tokenized into I one token, like one token, ice cream one token. The decoder then takes these hidden representations and generates an output sequence one token at a time based on the learned context. So we saw there are multiple ways where the decoder is learning the context, right? One is coming from the encoder itself, and one is coming from the decoder also had a multi-head attention below, whose output it was getting. So decoder was getting masked multi-head attention. Masked again means that you don't want certain words to have interaction. So basically these things we can probably cover in future sections. So this way it is learning the context, it is getting the input, and it is learning the context. So in short, okay. So this is all what we already talked about. So I'm not going to read all of this. Okay. So encoder decoder. So word embedding happened. Word embedding means you just translate the word into your numbers. Then your positional encoding, where in that particular statement, where in that sentence, what is the position of each and every word? You pass that also in the data. Self attention for each and every word sitting here, what is its relation to each and every other word? And how does it relate to? What is the probability that these two words come together? So you have an entire probability distribution of how these words sit in a sentence. Multi-head attention would mean that each and every word, how is it as a noun, verb, adjective, this. So you do that level of this also. So all of this and makes you understand the context very, very well. So this transformer is an encoder decoder architecture basically, and these are all neural networks, and the input comes in the form of this, and inside this you use self attention, multi-head attention to learn the context, and then you pass it through linear layer and softmax in the end to get the output, final output. Okay, finally we are coming to the good part now. So anything, any questions so far? Yeah, I knew you would all sleep. No questions?
No, Shubhanjali.
Okay.
Hi, ma'am. This is Soumya. Sorry to interrupt. Am I audible?
Yeah, you're audible.
Yeah. Thank you, ma'am. That was a wonderful session. I just had a query.
Mhm.
Can you please let me know if we have any limitations on the number of languages it can encode or decode? Do we have any limitations, or it can encode any language?
So that is what. So we have to train it on the data. So we are doing, so one is called supervised learning, right? Where you already provide it with labeled data. So you will provide it with 10,000 English language sentences and 10,000 French translations of that. And then you will train the model on that. So that would be supervised. You've already given it the output. Then we are also now with things, there is semi-supervised learning also, which is happening. And so there is a, I think it all only depends on how much of data it is there. It has to work on. We have to train it on that kind of data, but I don't think there should be any limitation. But that is what a lot of companies are working on. These translation, you have to provide it labeled data. Otherwise, it would not know what is the output, and it would not be able to uh, do that.
Hi, ma'am. Actually, I do have a
Got it.
small
Thank you.
doubt on
Yeah,
those
sure.
lines. Yeah, yeah. Like how well the distillation works in this space, and how it actually differs for use case specific models when we want to build a student teacher kind of model structure. Where this actually fits in the complete transformers game. With respect to a domain specific or with respect to any of the use cases which we are trying to build based on the existing leverage what we get from OpenAI.
So I think we will not have the infrastructure to actually train everything from scratch to even be able to make any model understand English or anything. So we already have pre-trained models, on Hugging Face, you will get it. You can download BERT from Google's, I think I'm forgetting, I think from TensorFlow or
That
someplace
part
you can
I'm like,
download.
yeah, that part I'm clear about it. My concern
Okay.
was like, what does this distillation actually means in this complete uniform of transformers architecture, where the distillation part actually comes in?
I didn't understand distillation meaning.
Yeah, exactly. Distillation of the model. So when you say when you can't put the complete architecture or retrain the whole structure, you kind of distillate the parameters or the weights and do
Okay. Like what
and
part can you feed and what part is already there and it's off the
yeah,
shelf
exactly.
and what
How
part can.
what how do you take a decision on top of it? That's where something I am also reading upon, and I don't find a proper solution so far.
Okay. So, see, in different enterprises also when they are doing the generative AI strategy, right? So there are because enterprise level or enterprise grade, you cannot feed your personal data into it, or you cannot feed your enterprise or clients specific data into it. But you do need a model which understands basic English. So what happens is that you take these different models. Uh, like whatever is available which has been trained by companies which has that kind of infrastructure like Google, Meta and Google and Microsoft. So you take those pre-trained LLMs, then you will have to run it or feed your own data into it. Then you need to have a team where you will have what is it called, reinforcement learning through human feedback, where each and every time. So what you do is you take that LLM, you bring it in your enterprise, or for your case if you are doing it for something personal, you buy it, you take it on your app or wherever, and then you feed data to it, and whatever it is answering, you will wrap it in some sort of a question answer thing, right? You will have to make a UI, you wrap it on question answer thing, and you say ask a question based on your data on it. And then whatever it is answering, you will have to have human feedback that it is right, it is wrong, or it is wrong, it should have been this. And then that goes back again in the model.
So it has lots of to and fro human intervention in all these
It has to have. It has to
oh,
have. If you have to fine tune it, so there is something called as Bloomberg GPT. What they did was they
correct.
took GPT and then they trained it on financial data, so that you can just ask it that okay, well, what about this stock? This you can ask it questions rather than doing the research yourself. So it was not answering everything the first time, because in finance, tender would mean something else, contract would mean something else, everything would mean everything else. So the humans have to initially make it, that's called fine tuning. So you will fine tune a normal very generic LLM onto your particular data. So that would need some human reinforcement,
Okay,
human
so there
feedback.
should be an altogether different configuration set up only to feed those human feedback
Right.
pipeline. Okay, I get it. I get
Right.
it. Thank you.
Yeah, sure.
Subhanjali, like I have a few questions. Thanks for the session, first of all.
Sure.
Regarding the architecture, right? There are like two flows in it. One is the encoder part, where like we give the input, we generate some sort of an encoding. When we say encoding, like we put across the embedding part, push encoding, and then we put self-attention. Other flow is when we say decoder, decoder takes output as an input, and then it transforms, it does the same process, and then it compares, and then when it compares, like it compares the probabilities. That's where like I'm having some question over there. I'm not getting the clarity over there. Can you just elaborate? Can you help me to understand?
You are saying that what is it comparing? What is the output that we are
Okay.
looking at?
So there are two flows in it, right? One like in the encoder
Encoder,
flow.
yes.
Yeah, in
Yeah.
the encoder flow, we are passing across the input, and in the decoder thing, like we are passing across the when you say output, basically the French sentences, right? French
Mhm.
sentences is the input. And the same process is followed over there as well. Finally, both the
Hmm.
things are being compared against. The feature vectors of both the things are compared against. And then eventually, like, it is optimized for in both the flows. Is it like both the encoder level and the decoder level?
Yeah,
That's my
yeah, yeah, yeah. So basically you get a you get a loss function in the end. Basically, you just want to minimize the loss in the end. So you keep propagating it back to both encoder and decoder till the time you find that your actual output is similar to the predicted output.
Okay. So both in the encoder flow and the decoder flow, both the output should
Yeah.
be same.
Yeah,
Okay.
yeah. The only thing that does not change in this is the positional encoding. Once you have the positional encoding, that will not change. You will not keep feeding that again and again. But the remaining things, it keeps getting optimized to go to a better this thing output.
Okay. Got it. Thanks.
Yeah. Okay. Okay. So let me go to that. Let me stop sharing for a while. Okay. So this will be everything that we have seen. Can you see my screen?
Yes, yeah, it's visible.
So generative AI exists because of the transformer, right? So this is the text. I will share the link of this. I think everybody should go through it. So see, you just have to see. You go to work by train. To write text, LLMs must first translate words into a language they understand. So this is what? This is word embedding. So first, a block of words is broken into tokens, basic units that can be encoded. Tokens often represent fractions of word, but we'll turn each word into a token. This could be fraction of words, but just for understanding, we are making each word into a token. So this statement is broken down into tokens. So in order to grasp the word's meaning, work in our example, LLMs first observe it in the context using enormous set of training data, taking note of nearby words. You see here, it keeps seeing work, where is work fitting, where is work fitting, where is the work fitting. So it is seeing it in context with nearby words to understand the context. These data sets are based on collating text published over the internet, which new LLMs trained using billions of words. So this keeps happening, right? So you have to understand the meaning of each word with the context. Eventually, we end up with a huge set of the words found alongside word work. Work was the word we were looking at. And we found a huge data set in the training data as well as those that weren't found near it. So we get two things: work atmosphere, work finish, work collaborative, work reward. And we found the words which are never closed. Work zebra, work dove, they are never closed. So the probability of this side is very less. The probability of this side is very high. As the model processes this set of words, it produces a vector or list of values and adjusts it based on words' proximity to work in the training data. This vector is called a word embedding. Okay. So work, this is a vector which will have probability based on what are the words which are nearby it and what is the probability of each of these words being nearby work. So you have a vector like this. The word embedding can have hundreds of values, each representing a different aspects of a word's meaning. Just as you might describe a house by its characteristics, type, location, bedrooms, bathroom, stories, the values in an embedding quantify a word's linguistic features. Okay, so if for this work, all its linguistic features, whether it's uh, you know a verb, it's this, all of that will be in this word embedding. The way these characteristics are derived means we don't know exactly what each value represents, but words we expect to be used in comparable ways often have similar looking embeddings. So sea and ocean will have similar embeddings because they are similar in a lot of ways, but they are different maybe in one, two ways. So you see here it is blue, here it is white, but we don't know exactly what this blue and white is representing, but we can understand that, okay, they will be somewhat similar. And all of this has been derived based on learning the context from that billions of data that it used to train on. So it got all of this, and it has all the words which have similar looking embeddings would be closer and like that, right? So till here we are good. A pair of words like sea and ocean, for example, may not be used in identical contexts, but their meanings are close to each other, and embeddings allow us to quantify that closeness. Because of embedding, we can quantify that closeness now, that they are more or less close to each other. So now by reducing the hundreds of values each embedding represents to just two, we can see the distance clearly between the words more clearly. So if you can see, if the embeddings vector would mean different dimensions. So now we have just put it in 2 dimension, but all that embedding means we cannot visualize it. For visualization, they have tried to put it in 2 dimension. So you can see that college, school, work, bus, car, they come together more or less, these things will come together. Now, so we might spot clusters of pronouns or modes of transportation, and being able to quantify words in this way is the first step in a model generating text. So this is just 2D that we are able to see, but then there are multiple dimensions in which the model is already doing these things which we are not able to see, and we don't even know what are the clusters. Here they have just, for understanding, put it in a cluster that we understand. But this alone is not what makes LLM clever. What unlocks their abilities? Transformer. Okay. So the transformers process an entire sequence at once. So what happens is context and patterns we get better and generate more accurately. And this is simultaneous, so it takes much faster. It happens much faster. For example, I have no interest in politics. A key concept of the transformer is self-attention. This is what allows LLM to understand the relationship between words. So self-attention looks at each token in a body of text and decides which others are more important to understand its meaning. Okay, each and every token with respect to others. Before transformers, the state of the AI translation were recurrent neural networks, which scanned each word in a sentence and processed it sequentially. With self-attention, the transformer computes all the words in a sentence at the same time. Capturing this context gives LLM far more sophisticated capabilities. So this is self-attention right here. In this example, assessing the whole sentence at once means the transformer is able to understand that interest is being used as a noun to explain an individual's take on politics. So because it could check the entire sentence, it could understand interest. But if standalone, if somebody just says interest, you don't know what they mean, but you need to understand the context. So that is self-attention. If we tweak the sentence, the model understands interest is now being used in a financial sense. So the model should be able to understand that also. And when we combine the sentences, the model is still able to recognize the correct meaning of each word thanks to the attention it gives the accompanying text. For the first use of interest, it is no, and in that are most affected. Okay, so here we have both interest, but because it knows the accompanying text, it was able to understand that they mean the different things. For the second, it is rate and bank. So this is what we were talking about, the attention that it has to give to which word is more important, like in that checker, in server and check, and server and crashed. So similarly here, this functionality is crucial for advanced text generation. Without it, words that can be interchangeable but not others can be used incorrectly. Effectively, self-attention means that if a summary of this sentence was produced, you wouldn't have enthusiasm used when you were writing about interest rates. So when it was generating on its own, it would not be used. The capability goes beyond words like interest that have multiple meanings. In the following sentence, self-attention is able to calculate that it is most likely be referring to the dog and not the bone. The dog chewed the bone because it was hungry. It means the dog was hungry and not the bone. And now how do you understand it? Because of its past training and the entire context. And if you alter the sentence, swapping hungry for delicious, the model is able to recalculate with it now most likely refer to the bone. So if you change it, it will understand that it is bone. So the context of the surrounding words is very important. The benefits of self-attention for language processing increase the more you scale things up. It allows LLM to take context from beyond sentence boundary, giving the model a greater understanding of how and when a word is used. So all these things it was able to understand that the dog had a red collar, the dog ate dinner at 6 p.m., dog was its owner's best friend, dog loved playing fetch. It was able to understand all of this from whatever text it had. So it had more data. So the more data, when you scale things up, when you put more data in it, so it will get more and more context and it becomes smarter. The LLM becomes smarter. So see, the Financial Times this is word embedding, positional encoding, self-attention. You have your encoded output. So after tokenization and encoding a prompt, we are left with a block of data representing our input as the machine understands it. Includes meaning, position, and relationship between words. This is the most important thing about the transformers, that you are putting the input, which includes meanings, positions, and relationships between words. At its simplest, the model's aim is now to predict the next word in a sequence and do this repeatedly until the output is complete. The Financial Times is, you just have to, with the maximum probability, what could be the next word, which would fit this context and which would grammatically and everything wise be. This is the only job that an LLM has to do. To do this, the model gives a probability score to each token, which represents the likelihood of it being the next word in the sequence. And it continues to do this until it is happy with the text it has produced. But this method of predicting the following word is known as greedy search, can introduce problems. Greedy search is just checking the exact next word. Sometimes with each individual token. So if you just see what is the next word, which is the best fit, so the next token might be best, but the entire sentence might just be very ambiguous. So transformers use a number of approaches to address this problem. One is beam search. So rather than focusing only on the next word, it looks for the probability of larger sets of token as a whole. So it will take multiple routes and find the best option, and not just the next word each and every time. So this produces the best results, ultimately leading to more coherent human-like text. Okay, so the remaining things I think you all can go through and read. I will probably put this link in the chat. It is a very good place to explore and see for it yourself. There is one more thing which I think you all should try. I will put this also in the chat. This is about, okay, this is your neural network. So you can just change the things here, your learning rate, your activation function, your ratio of training to test data, noise, batch size, your epochs, all these things, and then you will be able to see your output. So if you just keep trying to do this, and you will find it you will be able to understand. This is the original Transformers paper. In case you guys want to go through it, I took the diagram from here, from the original paper. So I will put that also in the chat. So any questions? I think we are very close to time, and I was not able to cover a lot of things properly, but I hope at least the basic understanding was clear. So any questions?
Shubhanjali, Saraswati here. No questions, but thank you so much. I think this was a very intuitive way of explaining in very simplistic terms. So thanks for the session.
Thank you so much, Saraswati. Thank you so much.
Hey, thank you so much, Shubhanjali. I think it was really informative. And thank you guys for joining. And I think if you have any clarifications, we are always there to help you out. I have just pasted the link and the email ID for you guys to reach out to us. So for any queries, any feedback, or if you have any other session that you have in mind or any topic that you want us to cover, feel free to drop an email. So Shubhanjali and I will take a look and we'll definitely get back with our next session. So share the link of our Women Who Code Chennai meetup and to your friends and all the passionate individuals. Have a great day. Thank you, Shubhanjali, once again.
Thank you all.
Thank you, Manjali. Thank you.